This is the second video in Chapter 4 dealing with centripetal acceleration and relative motion. Even though an object may have a constant speed, it can still have an acceleration. Even though its speed is not changing and so you have no linear acceleration, we can still have an acceleration due to the fact that its direction is changing. Here's an example. Take a look at this race car going through this curvature here. Its speed is not changing, so it maintains the same speed throughout the curvature. And if we look at its velocity vector as time progresses, we have this v1 going in one direction, and then a moment later it's got a v2 going in a different direction. So if we compare these two velocity as the vectors, we can see that there's a change in velocity between our direction v1 and our direction v2, even though the magnitude is still the same. So we have a change in velocity that's actually towards the center of this curvature, center seeking. This change in velocity is due to a change in direction, and the acceleration, which is this change in velocity over change in time, is center seeking, or what we say centripetal. We can look at this a little bit a moment later, where we have velocity 2 going in this direction, velocity 3 in this direction, and our change in velocity is again towards the center of this circular motion. So it's still center seeking. Here's another way to look at it. As we're going around this circle of some radius r, we have an initial velocity vi and a final velocity v sub f. And if we compare these two velocities, there's a change in velocity. So our initial velocity plus that change in velocity equals our final velocity. And that makes a triangle. It's actually a isosceles triangle because the magnitude of our initial and final velocities are the same. We also have another triangle here where our first radius and our second radius are bounded by our change in displacement, or our delta r. And that is a similar triangle to our velocity triangle. In other words, they have the same internal angles and the same ratio of sides. So they are similar triangles. Hence, the change in velocity to the magnitude of our velocity is equal to our displacement, delta r, over the radius of our curvature by the similar triangles. Hence, we can say our change in velocity is equal to our velocity times our displacement over our radius of the circular motion. So we can say that our centripetal acceleration is our change in velocity over our change in time, which is our velocity over our radius times our displacement over our change in time, which is the same as our velocity again. So we have a velocity times velocity over our radius, or our velocity squared over our radius. This is our acceleration due to our change in direction, our velocity squared over our r, which we call our centripetal acceleration, and it's directed inward towards the center of this circle, center seeking centripetal acceleration. So we have two accelerations. Our total acceleration will be the vector sum of these two. One is a tangential acceleration due to our change in magnitude, and the other one is a radial acceleration due to our changing direction. If we were to look bird's eye view at a car going down a road, it could be changing its speed, hence changing its tangential acceleration, and it could also be changing its direction, hence changing its centripetal acceleration. The two accelerations will be perpendicular to each other, and our net acceleration will be the vector sum of these two. So we'll have a total acceleration equal to our tangential acceleration plus our radial acceleration. Our tangential accelerations are change in speed per time, or change in magnitude per time. And our centripetal acceleration, or radial acceleration, is the value of our velocity at any particular moment, that squared, divided by the radius of curvature. They're perpendicular, so if we want the magnitude of our total acceleration at any moment, we could use the Pythagorean Theorem square the components, add them together, take the square root. So square our radial acceleration plus our tangential acceleration, and then take the square root of that sum. And that will give us the magnitude of the acceleration at any particular moment in this journey. Let's try this out. Here's a problem. The orbit of the moon about the Earth is approximately circular with a mean radius of 3.84 times 10 to the 8 meters. It takes 27.3 days for the moon to complete one revolution around the Earth. Find the mean orbital speed of the moon and its centripetal acceleration. So the moon's going around the Earth every 27.3 days in a sidereal period. Has a radius of 3.84 times 10 to the 8 meters, a mean radius. I don't know why we don't use the nice radius as opposed to the mean radius, but that's just the way we are in physics. So we're going to use the mean radius, 3.84 times 10 to the 8 meters, and that will give us a total distance traveled in 1 month of the circumference of this circle, 2 pi r. So our average orbital speed, our mean orbital speed, will be that total distance, 2 pi times the radius of this orbit, which is 2.41 times 10 to the 9 meters. And we're going to do it in 27.3 days in the sidereal period. So that's going to be 24 hours per day, 3,600 seconds per hour. So that's going to give us a total time of 2.36 times 10 to the 6 seconds. So the average speed of the moon going around the Earth is this total distance, 2.41 times 10 to the 9 meters, over 2.36 times 10 to the 6 seconds. The moon is traveling on the average 1.02 times 10 to the 3 meters per second. That's basically a kilometer per second. How about that? Rule of thumb. So if somebody asks you, how fast is the moon traveling around the Earth? 1 kilometer per second. What's its centripetal acceleration? That's its velocity squared divided by the radius of its circular motion. So that is 1 kilometer per second squared over 3.84 times 10 to the 8 meters. It has a centripetal acceleration of 2.71 times 10 to the minus 3 meters per second squared. This radial or centripetal acceleration is being supplied by the force of gravity between the Earth and the moon. What is the average speed of the Earth for one revolution around the Sun? Curious idea. If the Earth's going around the Sun, that distance is going to be 2 pi r, where r is the radius of the Earth's orbit, and it's going to do it in 1 year. There's approximately pi times 10 to the 7 seconds in 1 year, so we'll use that time. The radius of the Earth's Sun orbit is 1.5 times 10 to the 11 meters, or 150 million kilometers. So we have that the total distance the Earth travels is 2 pi times that radius over pi times 10 to the 7 seconds. Pi's cancel out. And we have that the velocity, average velocity of the Earth going around the Sun is 3 times 10 to the 4 meters per second, or about 30 kilometers per second. Pretty good. So about the distance between the Decatur and Huntsville, about 16 miles, if you will. That's how fast the Earth is moving in its travel around the Sun per second. So doing that distance, 1,001 per second. Good to know. Let's get back to a centripetal acceleration problem. Compute for a point located on the surface of the Earth at the equator the radial acceleration due to the rotation of the Earth about its axis. So, how fast are you moving, first of all, around the Earth if you were at the equator? Radius of the Earth is 6.37 times 10 to the 6 meters. The circumference of the Earth would be 2 pi times that radius. 2 pi times 6.37 times 10 to the 6 meters, almost by definition, should be 40 million meters, because that's how the meter was defined. There was 10 million meters from the North Pole down to the equator, and hence if you went the whole circumference of the Earth, that should be 40 million meters. And if you went the equator of the Earth, it's pretty close to 40 million meters as well. So we're going to travel 40 million meters in the time of one day, 24 hours, 3,600 seconds per hour. That is a speed of 463 meters per second. If you multiply that by 2.2, you would get miles per hour. Or another way to think about it is the equator of the Earth is 25,000 miles. And if you do that in 24 hours, you're going 25,000 miles in 24 hours. You're traveling greater than 1,000 miles per hour. In terms of radial acceleration or centripetal acceleration, that is your velocity squared in meters per second over the radius of your orbit or of your circle. 463 meters per second squared over 6.37 times 10 to the 6 meters for the radius of the Earth. That is a centripetal or radial acceleration of 3.36 times 10 to the minus 2 meters per second squared. This radial acceleration, which keeps you moving in a circle, is supplied by the gravity of the Earth. Hence, we can think if we were trying to measure g at the equator, a little bit of g is being used to keep you moving in a circle, and the rest of g is what you'd be measuring. So if you tried to measure the acceleration of gravity at the equator, you would actually measure not 9.80 meters per second squared, but you would measure 9.77 meters per second squared, because a little bit of this acceleration is being used to keep you on the Earth moving in a circle. More on that later. So that is an introduction to centripetal acceleration. We also wish to look at relative velocity and relative acceleration in this chapter as well. Consider a frame of reference moving to the right at a constant speed u, and you observe an event to happen. In other words, maybe you throw a ball at some velocity with respect to u in your moving frame of reference. We call that velocity v prime. Let's say we had an outside observer who's actually at rest on the Earth. So this outside observer is in what we say an inertial frame at rest, and you are in a moving frame. So we want to see what the rest frame observer would observe for the velocity of that tennis ball or baseball that you threw. They're going to see a velocity equal to the velocity that you threw the ball at plus the velocity of your frame of reference. So the two velocities are going to add, and the relative velocity to a person at rest is going to be the combined velocity of these two. The velocity of the moving frame of reference plus the velocity seen in the moving frame of reference. So that would be a combined velocity. So the velocity in the moving frame of reference will be equal to the velocity seen in the rest frame minus the velocity of the moving frame. So that is going to be, so v prime will equal the true velocity in the inertial frame minus the velocity of the moving frame. And position in the moving frame will be the position observed in the rest frame minus the velocity of the moving frame times time. So there's going to be a correction based on the fact that your frame of reference is moving. This correction, these relationships, are called the Galilean Transformations. They allow us to transform from a rest frame to a moving frame and still discuss velocity and position from these transformations. What about acceleration? Since we know that our moving frame of reference is moving at constant velocity, the change of that velocity with respect to time is zero. So our extra acceleration is actually going to be zero. Hence, the change of velocity as opposed to the event, which is throwing the baseball, that change with respect to time is going to be equal to the change observed in the rest frame for that same velocity per time. because there's no extra addition due to the fact that the moving frame of reference is moving at constant velocity. So acceleration will be observed the same way in both frames of reference. And hence any force that is causing this acceleration will be observed the same way in both frames of reference. So a moving observer with constant velocity will experience the same acceleration as an observer at rest. You won't be able to distinguish forces unique to both frames of reference. The Galilean transformation equations are valid only for unaccelerated frames of reference, what we call inertial frames. Also, these Galilean transformation equations are valid only at particle speeds that are small compared to the speed of light. Because if you get near the speed of light, which is the speed limit for the universe, you can't just go on adding velocities and keep on adding velocities because you're limited by the speed limit. So as you get to that point, near the speed of light, you have to use different equations to add velocities. And those equations are governed by Einstein's special theory of relativity. We will cover this in Physics 3 when we get to that point. All right, let's try a problem dealing with velocity addition. In this problem, we have a river that has a steady speed of 0.5 meters per second. A student swims upstream a distance of 1 kilometer, then swims back to the starting point. If the student can swim at a speed of 1.2 meters per second in still water, how long does the trip take? Compare this with the time the trip would take if the water were still. So we have the student is swimming at 1.2 meters per second. And to start with, we're swimming against the stream, which is at 0.5 meters per second. So the combined velocity will be 1.2 minus this velocity, 0.5 or 0.7 meters per second. We have to give a little bit of incentive to move fast here. Yeah, okay. So we have a shark on the tail. So we're going to move some distance x, and we're going to do it at a velocity in the rest frame equal to the velocity of swimming, the velocity of the student, plus the velocity of the stream, which happens to be in the opposite direction. So this is going to be, the magnitude of this velocity will be 1.2 meters per second plus a negative 0.5 or 0.7 meters per second. And we're going to travel that whole distance. So the time it takes to travel this first leg of the journey, 1 kilometer, will be 1 kilometer divided by our speed, 0.7 meters per second, or 1,429 seconds to do it. For the second leg of the journey, our velocities are actually adding together, helping us go downstream. So we have a combined velocity of 1.2 meters per second plus a 0.5 meters per second. Our velocity in the rest frame is actually 1.7 meters per second. And we're going to cover this 1 kilometer with that speed, 1.7 meters per second. It'll only take us 588 seconds to do the journey going downstream. So our total time to complete this journey going upstream and then downstream will be 1,429 seconds plus 588 seconds, or 2,017 seconds. Divide that by 60, and we get 33.6 minutes to complete this journey. If the water were still, we could go there and back again, 2 kilometers, 2,000 meters, at the velocity of the swimmer, 1.2 meters per second. That would be 2,000 meters and 1.2 meters per second is 1,667 seconds, or 27.8 minutes. So we could complete this journey faster if there was no river going. So even though we went pretty fast downstream, the problem was going upstream, and hence that slowed us down dramatically. In fact, you can think there would be a point where if the stream velocity were equal to our velocity of swimming, we would never make it upstream because the two velocities would cancel, and it would take us forever to complete this journey. So in that limiting case, it would take us too long to complete the journey, and we would never complete it. And here in still water, we could always complete the journey if we had any kind of velocity for swimming. So that's always going to be a lesser time to complete the journey, 27.8 minutes. So the difference between the moving stream in this case and the still stream is 33.6 minutes minus 27.8 minutes over our control of 27.8 minutes times 100%, 21%. So it took us 21% longer because the stream was moving in this case. But we could imagine a case where the stream, it would be infinitely percent longer if the stream were moving too fast. That completes the second lecture in Chapter 4 on centripetal acceleration and relative velocity, the Galilean Transformations.